Section 8.6 is polygons. And first, what in the world is a polygon? Well, it's a closed figure with a certain number of sides. So we're talking about things like squares and pentagons. Should have picked an easier one to draw. 5 sides, and triangles. And if you think about it, as long as the sides are straight, like I've attempted to do here, you have to have at least 3 sides, because you could have 3 like this, or 4, or 5, 6, 7, 8, 9, 10. But you can't go through and do a 2-sided object with straight sides and have it closed. So polygon, closed figure with, I'm going to write 3 plus sides. And each of those corners is going to be called a vertex. So there, 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 each of the ones here, the triangle, each of those called a vertex. So a point where 2 sides intersect. Or you could say meet if you want to. That's a little bit less mathematical of a term, I suppose. And then they're classified by the number of sides. So if we have a 3-sided one, like this thing right here, we'd call that a triangle. So triangle. 4-sided, might be tempted to say a square or a rectangle, and those are types of them, but all 4-sided objects, including parallelograms and trapezoids and stuff, those are quadrilaterals. The whole quad meaning 4, tri meaning 3. So 5 is going to have a similar prefix. It's going to be penta, so pentagon. Penta means 5, and you can maybe think of like the building for our defense for our country. Hexagon is 6, Hexagon. 7 is rare. I'm not going to ask you that one most likely, but it's a heptagon and an octagon. So it'd be good to know the names of all of those with the possible exception of heptagon. Now, we're going to have this section talk about just 3-sided things for a little bit and then 4-sided things. So 3-sided, if you have triangles. You take any triangle, at least until you get to like upper level geometry in college, but any triangle, if you take and add up those 3 angles, maybe I'll just write a 1, 2, and a 3. If you add those 3 things together, it adds up to 180 degrees. So if you know 2 of those angles, you're able to find the 3rd angle. That's where those questions are going to come up. Now, triangles, we can put triangles into 3 different classifications or categories. They're all going to either be equilateral, isosceles, or scalene. And for these, equilateral, you'll notice kind of has this equi in it. So it's going to be like things that are equal. So equilateral triangles are going to be, we'll see how good my drawing is, but it should look one where all the sides and all the angles are congruent is the math term, but technically you could think of it as equal. So those 3, you could put a dash on it. Those 3 sides are all the exact same length. So it's going to have 3 congruent sides. And all 3 of those angles should also be congruent. So I could take and say this angle is congruent to that angle, which is congruent to that angle. Well, if all the angles are the same and they add up to 180 degrees, 180 divided by 3 gives us 60. So we're going to have 3 60-degree angles. All right, the next one is isosceles. I think iso maybe means 2 or something like that, but isosceles triangles, I'll draw this next one a little bigger. That'll make it nicer to see. But it's going to have 2 congruent sides. And so 2 sides that are the exact same length. Usually they get drawn something like that, and then a horizontal base, horizontal-ish base. So we're going to have 2 congruent sides. I'll put the little hash mark in the middle, kind of at a 90-degree angle to the side, saying that those 2 are the same length. They're exactly the same. And when we have that then, this angle here, you'll notice, should be the same as that angle there. So it's going to have 2 congruent angles. And we can't say anything about the measurement there because we don't know what the measurement of that top one is. Once you know that, then you could divide the remaining number of degrees by 2. But we don't know, is it a kind of a skinny isosceles triangle like that, or it could be a much wider one, something like this. So we can't determine what those 2 angles have to be. All right, scalene. Scalene, all sides are different lengths. So I'm going to say 0 congruent sides, or just dash all sides have different lengths. And for that, you really could draw any triangle. You could do example, maybe do like a right triangle. So some right triangles are going to be scalene also. So something like that would be a scalene one, but you could also do like some weird shaped triangle, something like that here, some obtuse triangle. As long as the sides are not equal to each other, not congruent with each other, and they're different, and they're straight lines, you should be good. All right, so quadrilaterals. Quadrilaterals are done with triangles. We're going to switch to four-sided objects. And any four-sided object, I'm going to take and, if I were to have a four-sided one like this, I don't know if this is worth drawing, but I could take and break any four-sided object up into two triangles. So if I know this plus this gives me 180 degrees, and this plus this gives me 180 degrees, all those angles together give me the four angles of the quadrilateral. So 180 degrees plus 180 degrees gives me 360 degrees. So all four-sided objects, all quadrilaterals, the angles add up to 360 degrees. We want to kind of break these up into different categories like we did with triangles, equilateral, isosceles, and scalene. So a trapezoid is going to be the first one. A trapezoid for that, it's a quadrilateral, so that's my first dash. So it's a four-sided object with straight sides, it's enclosed. And it's going to have one pair of parallel sides. So when they say one pair, it means that two sides are going to be parallel. Usually when we draw those, people do a horizontal line and then a longer horizontal line below it, something like that. And then you could connect it with the other two sides. So then in this example, the top one and the bottom one are parallel. At least I tried to make them parallel. And then the two sloping ones on the sides are not. So that's a trapezoid. That's kind of the weird one of the quadrilaterals, or the one that's not similar to the rest. The rest are all going to fit into parallelograms. So I tried taking and breaking it up the rest of the notes kind of like this, at least section 4 of the notes like this. And a parallelogram is going to be the next part, and then we'll look at rectangles and rhombi or rhombuses as being like special parallelograms. So parallelograms now, first thing is they're going to be a quadrilateral. So quadrilateral, but now we have two pairs of parallel sides. So usually when teachers or books draw this, they'll do something like this here, and then they'll draw the other side something like that. I think my bottom's sloping upward a little bit, so that might make it look a little bit better. And so a parallelogram would be something like that. Now we could have two different types of parallelograms. One is going to be a rectangle. So the rectangles here are all going to have 90-degree angles. So if we have 90-degree angles in a parallelogram, it's kind of like this thing here gets kind of scrunched up this way and makes it into a rectangle of sorts. So it's a quadrilateral and a parallelogram, any rectangle, but it's also going to have 4 right angles. And so rectangle, usually we make them wider than we do tall. And so I'm going to do a rectangle like that and put in that all the angles are 90 degrees. So there's a rectangle. Now a rhombus is going to be similar in that it's a type of parallelogram, but now our angles aren't going to be 90 degrees. So these are often what people kind of think is like a diamond shape, so not 90-degree angles. But something's true about the sides. So it's a quadrilateral and a parallelogram, but it has 4 congruent sides. So the rectangle has 4 right angles. This is going to have 4 congruent sides. So in other words, all the sides need to be the same length. So if I make my parallelogram, my one up above actually looks pretty much like a, I'm having trouble drawing on the bottom of the page with my iPad. So something like that there, this, and this. Put on my little hash marks to show that they're all the same. But something like that would be a rhombus. And it could be like that. It could be made skinnier, you know, something like this here. But a lot of times it's kind of what you'd think of maybe as like a diamond sort of shape. So rectangles and rhombi or rhombuses, those are both types of parallelograms. Now if we have a square is going to fit under both a rectangle and a rhombus. So you could take both of these then and combine them together to get your square. So a square is like the best of both worlds. It has the 4 right angles. I'm going to do that in green, like my rectangles in green. But it's also going to have 4 congruent sides, like my rhombus has the 4 congruent sides. So a square, go ahead and draw that like you've been doing for years. See how I can do here. I'm going to try to go slow and be careful to get sloppier. So I have my 4 90-degree angles, and I have my 4 congruent sides. So that's my square. All right, we're getting close to the end. We're up to Roman numeral 5. So the last page of the notes here, I believe. And so classifying polygons, a diagonal, first we need to kind of define that, connects 2 vertices. And if you think back to page 1, vertices are the corners. So vertices, that's plural for vertex, that don't share a side. Now I'm going to erase all these in a minute, but what I'm trying to say is this here would be a diagonal, this would be a diagonal, this would be a diagonal. Those are diagonals, but you can't have diagonals that are going to like go from this vertex to that vertex, because that's not a diagonal, that's just one of the sides. Okay, so a convex polygon, the reason we had to say what a diagonal was, is if you take a convex polygon like this, all the diagonals, I guess I didn't have to erase it, but all those diagonals are going to be, you'll notice, inside the polygon. So all diagonals are inside the polygon. Where if we have a caved-in side or a concave polygon, at least one diagonal is going to be outside. So some are inside. You know, if I were to draw this one here, that's inside, and this one's inside, and this one's inside, and so on. But as soon as you get one of them, that's outside, then you know it's concave. So at least one diagonal is outside the polygon. So that for concave polygons. Now regular polygons, all sides and angles are congruent. So are congruent. And that's just a fancy math word of saying equals. So something like this is going to be a regular polygon. It looks normal. So when you think about like polygons, what does a pentagon look like? You're probably picturing a regular one. So this one here is regular. This one here is irregular, because this angle here is quite a bit smaller than that angle there. So that one's irregular. All right, so for the sum of the angles then, here's an equation that you can use. So sum, capital S, equals 180, as in 180 degrees, times n minus 2 in parentheses. So that right there is going to be the sum of the angles, or the total number of degrees, and n is the number of sides, as written there in black. So if you wanted to do this, you could go through, and for this rectangle here, so it's 180 times n minus 2, and s equals that. Well, that's going to be 180, and the number of sides is 4, so it ends up being 180 times 2, or 360 degrees. Slide that up a little bit. And we could do the same thing for the one next to it where we have the pentagon. So write the equation, s equals 180 and n minus 2. Now in this case, if we count them up, we have 5 sides. So we put a 5 in for n. So we get 180 times 3. So that'd be 540 degrees. Last one here, we have 180 n minus 2. Now we have a 6-sided object. We have a hexagon there. So we have 180 times 4, which will be 720 degrees. Now, if you think you might forget this, here's another way you can do it. We said that each triangle is 180 degrees. Well, if you take this here, I have two triangles. This one's 180, this one's 180, which makes sense then that we'd have 180 times 2. This n minus 2 tells us how many triangles you have inside your object. This one here, I do a triangle there and a triangle there. We just need to make sure that we're not connecting anything in the middle. I have 180 here, 180 there, 180 there, or 180 times 3. So push comes to shove, if you're totally feeling stuck on a test, you could go through and figure out how many triangles you get. And it'll always be 2 less than the number of sides. That's how the equation works. So I have 4 different triangles, which is why it's 180 times 4. That's it for the section. Sorry it's a longer one. Let me know if you have questions. But those learning targets are what we should have learned. So have a good one.